Buenos días, soy Andrew Campbell, estoy Business Development Manager en la empresa Cloud Seeding Technologies, ubicada en Alemania, en Europa. Voy a darles mi presentación en inglés. Hablo un poco de español, pero hace mucho tiempo que lo practico. Conozco también un poco Argentina, sí que tengo la historia con ustedes en Argentina. Hoy día les voy a contar un poco sobre la tecnología que llevamos nosotros desde nuestra empresa. Y se trata de Cloud Seeding Flares, como se llama aquí, o mejor dicho, bengalas y cartuchos, como se llaman en Argentina. Y ahora voy a cambiar al idioma inglés para poder continuar con la presentación. For the English speakers among you, my name is Andrew Campbell. I work at Cloud Seeding Technologies based in Germany, in Europe. And today I'm going to talk to you for about half an hour about the flare technologies which one uses in cloud seeding operations around the world. Thank you for your attention, and I hope you enjoy the presentation. So firstly, I'd like to tell you a little bit more about our company. Cloud Seeding Technologies was formed in 2017 as a subsidiary of FK Aviation, which is a cloud seeding operator operating in Central Europe. We provide a range of solutions to cloud seeding operators all around the world. And those solutions comprise flare systems, also other systems associated with cloud seeding operations, and a number of services to different operators in different countries around the world. We pride ourselves on having our own in-house research and development and design and production of all of our systems. And one of our key factors in the way we do our business is that we collaborate with universities who are specialized in the background sciences to cloud seeding, in particular some top universities in Europe, in Switzerland and Germany. So getting to the subject itself, firstly, I'm not going to dive straight into the subject of flares, but just spend 1 or 2 minutes on the context. I know you will have heard something about this as well in other presentations, but just to put everything into context, I'm going to talk about why do we see clouds? And it's all about affecting the way that water or ice present in clouds behaves. And we could want it to behave, for instance, to alleviate drought in situations where there's too little water, or there are even situations where there could be too much water. For instance, in an open cast mining operation where it rains too often, one could try and delay the rainfall or divert the rainfall to another area so that your operation can continue. You could want to suppress hailstones falling to the ground, in particular very large hailstones. And I know that in Argentina, this is one of the problems which is quite prevalent there. And the cloud seeding program in Argentina focuses to a large extent on suppressing the creation of large hailstones. And why do you want to do that? Do you want to prevent damage to agricultural crops, but also prevent damage to personal property like cars, houses, any other property outside in the open air? And lastly, what has also been done in some places around the world is to use cloud seeding to reduce fog or smog on, for instance, airfields, on highways, and in some cities which suffer from major smog problems. So how does cloud seeding work? Basically, it comes down to the injection of artificial aerosols or particles into clouds to accelerate and to increase the formation of what we call hydrometeors. And those hydrometeors are ice crystals, raindrops, or snowflakes, depending on the meteorological conditions which you're dealing with. It's useful to distinguish also between cold cloud seeding and warm cloud seeding. Cold cloud seeding is the case where the temperature in a cloud is 0 degrees or lower. And in warm cloud seeding, we're talking about conditions where the temperature in the cloud is above 0 degrees centigrade. So the water exists as a liquid and not a vapor or ice, for instance. It's also useful to distinguish between the two main categories of the application of cloud seeding. One is from the ground using what are often called ground generators, and the second is from the air using aircraft. And with aircraft, you can think about either seeding from the top of a cloud or above a cloud, or from below the cloud. And in the case where you seed from above the cloud, you use one type of flare technology that we would call, in English, we call ejectables. And in Spanish, you would call cartuchos. And in English, when you seed from below the cloud, we use burn-in-place flares, or bengalas, as they were called in Argentina. This slide here gives you a complete overview of the whole range of flare types and technologies involved in seeding clouds. And as you can see, the table is divided into the blue area, which talks about cold clouds, and the red area, which talks about warm clouds. And associated with each, there's a particular name. So for cold clouds, we talk about glaciogenic seeding, which deals with creating ice particles in a cloud, versus in the warm cloud case, hygroscopic seeding, which talks about attracting water vapor to particles to then create cloud droplets, which then turn into raindrops. And there's all kinds of categories, as you can see here. So I talked about ejectable flares, I talked about burn-in-place flares, I talked about ground-based generators. And there are also aircraft-mounted generators. And in the two cases of ground-based and aircraft-mounted generators, we're normally talking about using liquid materials to generate the particles, which are then emitted into the air. And in all the other cases, the flares, both in the glaciogenic and in the hygroscopic case, we're talking about flare bodies, which contain solid compounds, which are burned to generate particles, except the very last flare on the slide to the very right, which we call pneumatic flare, which is actually a flare which does not burn pyrotechnically, but is actually composed of pre-milled powders, and those powders are ejected into the cloud in a powder form, in their native form immediately. Just a little bit about CST flares and the ones we produce ourselves. We believe that we have a best-in-class solution. And that's really due to the fact that we continuously develop our products as we speak in our in-house facilities. And we've been able to create and maintain the most technologically advanced cloud seeding reagents on the market. They are very versatile. We can package them in different ways. They're very effective and they're very reliable, which is certainly one of the issues which one encounters in the marketplace. Given that we're dealing with pyrotechnic products, which are explosive in nature, safety is a very important aspect, and we pride ourselves on our very good safety record, and that's down to the way we produce our materials. All of the products we produce are designed, tested, and continuously improved using our facilities in Germany and Switzerland. And as I mentioned before, we do business all around the world. Just quickly mentioning where we do business, we have customers in Germany, in Switzerland, Austria, Slovenia, Romania, France, Spain, but outside Europe, we also do business in Malaysia, Indonesia, and South Korea, and hopefully sometime in the future in Argentina. So I talked about glaciogenic flares, which are for cold clouds, and I talked about hygroscopic. I'm going to dive into a little bit more detail to explain more about the way that flares are made, using the case of glaciogenic flares. So these are for cold clouds. The way to achieve the most effective result with glaciogenic flares is to take account in a very explicit way of the following factors. Firstly, the reagent, as we call it, the critical ice-forming chemical in a flare, needs to be developed in the right way. And it needs to be mixed with the most effective pyrotechnic compounds, so the compounds which you're going to use to to burn in the flare, which then leads to the creation of the aerosol particles. In doing all of this, one needs to take account of the operating conditions in which the flare will be used, and that's about the temperature, the pressure, the humidity conditions in which the flares are going to be used. And last but not least, the physical design of the flare is also very important, as that can have a large effect on the result and the performance of the flares which you use in your operation. So I'm going to look briefly at each of these four aspects and talk to you about what we believe is the best practice for creation of flares. Very quickly, though, a little bit about pyrotechnic flare principles. So this is a very simple diagram to show very roughly how one makes a pyrotechnic flare. Firstly, you create a pyrotechnic base compound, which you then mix with an active seeding reagent. In the case of cold clouds, the base seeding reagent is something whose key element is silver iodide. And silver iodide has the property of attracting ice crystals to it, which then lead to formation of more ice crystals and larger ice crystals, which then eventually lead to precipitation. In the case of warm cloud seeding or hygroscopic seeding, the silver iodide is not used, but different kinds of salts are used. And sometimes it's even as simple as using what we would call table salt, which you and I have on our dinner table at mealtime. These are mixed and packaged in a flare casing or body. They're ignited, normally by means of an electric igniter. And these cause the flare compounds to burn, so the mixed compounds of pyrotechnic base products and the seeding reagents burn, and they create the aerosol particles, which are then spread into the cloud. To give you a rough idea of how many particles we're talking about, these are very high volumes of particles. So the flares we produce, you could be thinking about several billions of particles per gram of the pyrotechnic mixture in the flare. So per flare, we're talking about many tens of billions of particles which are injected into a cloud per flare. So coming back to the ice forming reagent. So we've managed to take the basic silver iodide reagent formula, which, to be honest, has existed for some time, was developed in the mid-1900s. But the challenge which was faced by a lot of producers was that the optimum mixture leading to the best results of ice forming in clouds was very difficult to produce. So we've managed to come up with a production method which is effective and reproducible, so that we can reliably produce the best adaptation of that original formula and create our flares with that. The result of that is that we've increased the range of operation of glaciogenic flares closer to 0 degrees than any other system has been able to do up to now. Typically, most flares which are operating glaciogenically would only start being effective at -4 degrees centigrade and then go to colder temperatures. But our flares are able to become effective at a warmer temperature of -2.5 degrees centigrade, which can have a big impact on the number of aerosol particles which are injected into the cloud. So that means that the yields in our flares are greater than one would typically find in other systems available. And of course, the bottom line is that delivers a higher rate of ice formation in the clouds you are seeding. So that's the first point, getting the chemical compound right for the seeding reagent itself. Second point is creating the most optimum pyrotechnic compound. Traditionally, pyrotechnic compounds for cloud seeding flares have been created using a mixture of dry materials, which have then been pressed into flare casings manually. The issue with that has always been that the pressing process has never been perfect. So a lot of systems have suffered from remaining small interstitial spaces between the particles in the flare, which means air is still present in the flare, which means that water can also get into the flare. So those those effects can lead to degradation of the quality of a flare, but they can also lead to issues around safety. So spontaneous detonation has been a problem with some products. And we avoid all that by actually not using dry materials, by not pressing them into the flare, but by creating a mixture which is based on liquid polymers, which we then mix with the active reagents and we pour as a liquid into the flare and allow to dry. And the result is that there's no air left inside the flare, there are no troublesome interstitial spaces, there's no penetration of water, and there's really no issue with safety with this kind of design. And it also leads to a very long shelf life. So we're able to guarantee that our flares will remain effective for at least 10 years if stored in the right environment. So we've talked about the reagents themselves. We've talked about the pyrotechnic mixtures. Now let's talk about the operating environment and the flare design aspects, which are also important for the end result in terms of performance of your flare product. So let's take the case of ejectable flares. So as I mentioned, ejectable flares are injected into clouds, normally above a cloud, only the top of a cloud, and they burn as they fall through the cloud. And they typically would fall at a speed of around 30 meters per second. A typical injectable flare would burn for about 40 seconds, which means it would travel a distance of around 1,200 meters. Through that 1,200 meters, you can expect a significant change in temperature from the coldest parts of the upper cloud to the warmer regions of the lower part of the cloud. And the challenge is really, how can you achieve the maximum performance with a flare which is undergoing that change in temperature from top to bottom? Ideally, you would want to develop a flare there which would perform well both at cold temperatures and at warm temperatures. And we think we've managed to do that. And the way we've done that is to develop a flare with what we call two burning modes, which essentially follow two paths as are shown in this graph. So if you look at the top right of the graph, you can see on the green curve, we achieve a very high performance at the coldest temperatures. And as our flare burns, it changes mode halfway, such that we effectively switch to the blue curve, which flattens the curve on this graph and maintains a higher level of performance, a higher level of particle creation than other systems available on the market. Let me show what I mean in terms of photographs. This shows a number of different flares in a test environment. The third flare from the left is basically the design we're talking about, the dual mode flare design. And you can see the flare tube is in two parts. The first part has some specially created small nozzles in it, which create a certain size of particle, which is the first mode of operation. As the flare burns down, it switches over to the second half of the cartridge and burns in a different way, which creates a different particle size, which then creates the optimal particle sizes for the temperature regions in the cloud as the flare has fallen down. And here's some more detail on the different flares themselves. On the left here, we show, for comparison purposes, what a standard ejectable flare would look like, which does not have a dual mode construction, but only a single mode. So at this moment, I'd like to switch quickly to a YouTube film. Hopefully you can see it and hear it as I play it. And this is an example of our dual mode flare in operation in our test environment. And you'll see hopefully the two modes of operation which I mentioned before. The first half burning. You can see the small nozzles here, which will emit the smaller size particles for the first half of the process. And during this process, the size of the particles emitted through those nozzles is smaller, which is optimized for the colder temperatures. And when it reaches halfway, the first half drops off, and we move into the second mode of operation, where the particles are larger, which is ideal for the lower, warmer regions of the cloud. This photograph is an example of how ejectable flares are mounted. So they are typically mounted underneath the fuselage of a plane. And the equipment you can see here, hopefully you can just make out a number of holes in the underbody of the box, which is mounted on the plane. And at each of those holes, each of those compartments, we would mount a single ejectable flare. And the pilot then, who is performing the cloud seeding operation, will manually control the sequence and the timing of the ejection of those flares by means of a control panel inside the aeroplane's cabin. And that will send then a signal to ignite these flares one by one, which are then ejected into the cloud. So let's talk about burn-in-place flares. We talked about ejectable flares, which are ejected into the top of the cloud, which fall down and burn as they descend. A burn-in-place flare is typically mounted on the side or under the wing of a plane. This shows the example of mounting on the side of the plane. And these remain connected to the plane. They burn in place, as the name suggests. And they are spread into the cloud as the plane flies underneath a cloud. In this process, we rely on updrafts, which are present underneath the cloud, which would typically be in place under storm conditions or the meteorological conditions in which you would want to seed. And the updraft would transport the aerosol particles into the cloud, where they would take effect on the cloud composition. So again, we were talking actually about the overall flare design and taking account of the conditions under which you would seed. And just as in the ejectable flare case, there are considerations which are very important with burn-in-place flares. And the critical one here really is about the type of casing you would use. Traditional systems have up to now used casings which do not burn as the flare burns. So they've actually remained in place, and the substances inside the flare have burned down. But the issue which they've experienced is that a certain percentage of the overall volume of the flare is not actually able to exit the flare body. And that reduces then the efficiency of the process, and up to what we've measured to be around 6% reduction in overall performance, because basically a lot of the materials remain inside the flare. So this shows a photograph of a standard burn-in-place flare after burning, where you can see that the flare body is still actually intact, and we've retrieved some of the materials which are still inside the flare, which have remained unburned and therefore unavailable for the seeding process. The way we've approached this is to create a flare with a fully combustible body, meaning the flare burns in its entirety. So these photographs show the process of a CST flare burning from start to finish. And you can see that the flare body burns along with the flare materials themselves, which means that there's only a very slight, if any, reduction in the productivity of the flare as it burns. So let's recap. We talked about the reagent itself, we talked about the pyrotechnic materials, we talked about the conditions, and we talked about the flare body design. All four factors are very important when designing flares and producing flares if you want to maximize the effect. And I've told you about the example of glaciogenic flares for cold clouds. Let's look very quickly at hygroscopic flares, which are used in the warm cloud case. These are the types of bodies which we have brought to market. So on the left, we have a pyrotechnic option, which we've just talked about in the glaciogenic case. And we also have a powder option, which is in effect a pneumatic mechanism, which also has a small element which burns, but in fact burns to eject the powder contained in the flare in one go. So there's no slow burning process with a powder flare. There's a very quick ejection process. So here I'd also like to show you a movie which demonstrates how this works in practice. And I'm going to show you a film which shows the test of two different sizes of pneumatic powder flare in our test facility in Germany. And it shows, you should be able to see quite easily how there's a small explosion which is followed by the ejection of the powder. So I've come to the end of my presentation. I've given you a quick overview of why we seed, what kinds of materials and systems are used when seeding. I've talked about the difference between cold cloud seeding and warm cloud seeding, and I've talked about the different types of flares you would use in the different cases. It's been a very quick journey. Clearly, there's a lot more detail to this. I'd be very happy to answer any questions you might want to send me by email or using the links made available to you by the NASA Apps organization. I thank you for your attention, and I wish you a lot of interesting talks after this. I hope you enjoy the rest of the sessions. Thank you very much, and goodbye.